Hi everyone, and welcome to Chapter 7 on probability and samples. Previously, we've discussed using a z-score to find the probability of that score. We asked ourselves, what is the likelihood of having that score or outcome when compared to all possible outcomes? But that only works when there is one score. However, as you've learned, we typically sample multiple people from a population, resulting in many scores. So what do we do? Well, instead of calculating a single z-score for one data point, we can calculate a z-score from a sample mean, which would allow us to have a z-score that describes the entire sample. To give you a visualization of this, we have a population of people, and we take a sample from that population. We can then calculate a mean of that group and create a z-score of that mean to examine its probability. However, we run into an issue here because the people we sample usually don't represent the population perfectly. Say you're interested in depression scores in the United States, and you provide a depression questionnaire to a sample of people living in the United States. It's possible that just by chance, the majority of people in your study have major depressive disorder, and the mean of that group is greater than the mean of the population. Or maybe the opposite is true, and your sample has lower depression scores from that of the population. Either way, there's some error between these groups. We call this sampling error, which is defined as the natural discrepancy, or amount of error, between a sample statistic and its corresponding population parameter. As stated in that definition, sampling error is natural, and while we can try to minimize it, it's just something we have to account for in research. Here's an example of sampling error that was shown in the Chapter 1 lecture. We have a population of 1,000 college students. The population has an average of 21.3 years, an average IQ of 112.5, and is 65% female, 35% male. Say we take a random sample of 5 people, and we get Eric, Jessica, Laura, Karen, and Brian. This group has an average age of 19.8 years, an average IQ of 104.6, and is 60% female, 40% male. The sample is similar to the population, but as you can see, there is some error here. Say we did this again, and we took another random sample of 5 people. We get Tom, Kristen, Sarah, Andrew, and John. This group has an average age of 20.4 years, an average IQ of 114.2, and is 40% female, 60% male. Again, the sample is similar to the population, but there is some error. Because 2 different samples taken from the same population will likely have different means, it's important to look at the distribution of sample means. The distribution of sample means is the collection of sample means for all the possible random samples of a particular size, or n, that can be obtained from a population. For instance, take a look at this distribution of people. Say this is your entire population of interest, and their scores fall into a normal distribution. Then say we take a sample of that group and we plot it. Then say we take another random sample and find the mean again. And if we do that over and over, plotting the means, we get the distribution of sample means, which is normally distributed and roughly equal to the population. So when we keep sampling people, we get closer to characterizing the population itself. Therefore, most of the means will be near the true mean of the population, and the larger the sample size, the closer the mean should be to the population mean, and the less error there will be. So larger samples are typically better in research because it helps us to minimize that error. So how do we calculate that error? In statistics, we use standard error, which is the standard deviation of the distribution of sample means. This is notated as sigma subscript m equals sigma divided by the square root of n. And at this point, you're likely familiar with these symbols. Sigma is the population standard deviation, and n is the sample size. You can also calculate this by using the equation sigma subscript m equals the square root of sigma squared over n. You can see that this is essentially the same equation, but it allows you to plug in everything at once if you have a scientific calculator, and it can help to minimize rounding error, but either is fine for this class. This equation just helps to simplify that process. One thing to note is that the sample size is in the denominator of the equation, which means that the greater the n, the smaller the standard error. Again, showing that an increased sample size minimizes the difference between the sample and the population. Here's an example of finding standard error for a population standard deviation of 25 and an n of 100. Using the first equation, we just plug in the numbers and we get 25 over the square root of 100, which is 25 divided by 10, and equates to 2.5. Or we can use the alternative equation, which gives us the square root of 25 squared over 100, which again is 2.5. Here's an example for you to try on your own. Find the standard error for a population standard deviation of 15 and an n of 22. The answer will be shown in 5 seconds. Using that first equation, we have 15 divided by the square root of 22, which is about 3.2. Or using that alternative equation, we have the square root of 15 squared over 22, which again is about 3.2. From here, we can get back to that original task of obtaining a z-score for a sample of participants, which is very similar to our previous z-score equation. To do that, we have the equation here with m, the sample mean, minus mu, the population mean, divided by sigma subscript m, which is the standard error. But as you'll notice, you might need to solve for the standard error to find the z-score, depending on what information you're given. Here's an example of finding a z-score for a sample when the sample mean is 25, the population mean is 15, and the standard error is 4. Using that equation, we just plug in the numbers, which gives us 20 minus 15 divided by 4, or 10 over 4, which is 2.5. Here's an example for you to try on your own in which the standard error needs to be calculated. The sample mean is 25, the population mean is 26, the population standard deviation is 4, and the sample size is 25. Pause to solve. The answer will be shown in 5 seconds. In step 1, we need to find the standard error. You can use either equation, but I chose to use the alternative equation here, which gives us 0.8. In step 2, you can plug in the information to find the z-score, which gives us 25 minus 26 divided by 0.8, which is negative 1.25. Once you have the z-scores, you can find the proportions or probability the same exact way using the unit normal table discussed in the previous chapter. But what if you're trying to find the proportion between two z-scores? This is something we haven't talked about yet. We've talked about mean to z, such as with measuring the proportion from 1 to 0, but we haven't talked about measuring proportions from, say, negative 1 to positive 1. So what would we do here? To do this, you would just combine the proportions together. Step 1 would be to find the mean to z for each score using column D of the unit normal table. Step 2 would be to just add the numbers together. Using that example given, if you were asked to find the proportion of z-scores between negative 1 and positive 1, you would look at the unit normal table and see that the proportion is 0.3413 between the mean and 1. And since these are the same number, this is the same proportion for negative 1. but if you had a different number, you would have to look that up separately. Adding these numbers together, you would get 0.6826. We won't draw these by hand in class, but know that error is a big deal in research, and the majority of graphs you'll see in your field will have error bars on them. So you can see the amount of error which was calculated for that data. The bars extend one standard error above and below the mean. And as you know, the smaller the error, the more closely related the data is to the population. Again, some error is natural and to be expected, but we do want to minimize that where possible. So looking at this graph, we would probably trust the data from category B more so than that of category E. And you will calculate error bars later on using JASP. But that is all I have for you. If you have any questions, please let me know.